Hello. So in this lecture, we're going to look at policy gradient methods. And these are essentially methods that learn a policy based on the gradient of some performance measure. So when we were looking at value-based methods, what we said was that, well, for instance, we had an agent in an environment and we're trying to find the ways that the agent can act in the environment, but we did that by first estimating the value of being in different states of that environment. And or it could be values of being in different states or state action pairs. And based on those value computations, we essentially derive the policy or how we act in that environment. However, with policy gradient methods, well, in principle, what we're trying to do is learn this policy directly without essentially learning the value functions first or anything of the sort. So in this particular lecture, we're going to introduce the policy gradient theorem, and based on this, we're going to actually derive our, well, let's say our future reinforcement policy-based reinforcement learning algorithms. So having said that, let's actually get started. So the first thing is we need to actually see how we would represent this function. So when we're thinking about our policy function, we look at pi of a given s parameterized by theta, right? So, and we just need to ensure that this function itself is differentiable. So you should be aware of what this function means if you've been following the lectures. This is essentially the probability of taking an action in a given state, except that we're now parameterizing this by theta so that we can essentially use some metric to find the value of theta that maximizes whatever metric that is. So before actually getting ahead of ourselves, let's first ask the question how do we define optimal policies? Because in tabular learning, a policy is optimal if it can maximize every state value. That's how we defined our optimal policies back then. But now our policy function is represented by theta, right? So as you can imagine, you would expect us to compute some gradient computations in order to maximize some metric that we will define. So let's say that we are using a metric called j theta, right? And this is a scalar matrix that defines our optimal policy, right? So let's say j theta is a scalar matrix that defines our optimal policy, right? So, and we know that essentially this theta here, this essentially defines our policy, right? Because as we change the value of theta, then our policy changes, right? So this is the parameter we're trying to control in order to determine the optimal policy we should have. So we have some scalar metric that defines our optimal policy, which we define as j theta. So the way we would update theta would be to say theta at time step t plus 1 is equals to theta at time step t plus alpha times the gradient, right, of theta of j theta t, right? So right now I have not specified what j theta actually is, and I will do so in a moment. But the point here you're supposed to get is that this is an optimization objective. We're trying to maximize this metric that defines our optimal policy, right? So the higher it is, the better. So we do a gradient ascent step, right, on our theta values here. So this is gradient ascent, right? Which is different from the gradient descent algorithms where we would essentially subtract the value here because we were trying to minimize something. So because this is a maximization objective, that's why we're doing gradient ascent instead of gradient descent, right? So now what metrics can we then use to define optimal policies? So what we're asking here is what values of j theta could we use to define what our optimal policy is? So I'm going to just go through a few different values of j theta that we could use, or a few metrics that we could use. So the first one I'm going to go through is called the average state value. So we're going to start with the average state value. So what this average state value says is, okay, so we look at v pi, right, which is our value function, and let's say this is defined as follows, right? So we have our value, well, like v pi is essentially like a vector of state values, right? So let me actually write that here. So this is a vector of state values. That's what v pi is. And then we look at another parameter called d pi, right? And this is another vector. But what this vector is a vector of weights, right? So what are these weights for? Weights that are indicating how important each state value actually is, right? And the assumption here, I'll just write that in a different color, would be that the summation over all s of d pi of s should be equal to 1, right? That's what we would be going with. So what is our average state value here, right? So we define that by saying v, let's say v hat of pi, which is equal to d pi transpose v pi, right? Which is essentially the summation over all states of d pi s times v pi of s, which is, as you can see, the expected value of v pi of s, right? So that's how we define our average state value. So again, these weights are just, this is just a vector of weights to just show like how important each state actually is, right? Because some states are going to be more important than others. And how we actually determine that, we're going to look at. And the other thing here is that, okay, we define our average state value. So this is essentially the metric that we try to maximize, right? So we're trying to maximize this metric here, well, in this instance, to actually learn our policy. So we'll be adjusting our data in order to maximize this metric, because if we maximize it, then that means that we would be learning an optimal policy based on like whatever the values of this states actually are. So the question now is, how do we decide, right? How do we decide on v pi of s? Right? How do we no, not v pi of s. We already know what this is. I mean, on d pi of s, our weights, right? So one representation of this. So one representation of this would be to say, so number one, we could say d pi of s is equals to 1 over the cardinality of s. So here that just means we're treating each state equally. We're not giving the states any kind of preferences. But of course, like this is a huge assumption to make because in most problems we'll find out that some states are more important than others in any case. But another way we could do that is to say, we say d pi satisfies a stationary distribution as follows. So it would be like d pi transpose p pi is equals to d pi, right? So it satisfies a stationary distribution with the following property, and this here would be the state transition probability matrix, right? So if this is not making sense to you right now, that's fine. like the point, there's an entire derivation of how the stationary distribution is. I'm not gonna go through that right now. I'll do that in a future lecture. But right now, what you need to know is that the stationary distribution just reflects the long-term behavior of our Markov decision process, right? So what that means is that if one state is visited frequently in the long run, then it is more important and deserve more weight than less visited states and so on, right? But we're gonna go through like all of these like things in like a future lecture. Right now, I just want us to focus on the like on the objective, which is we want to maximize some metric and how we actually go about doing that. So we've defined our first metric here, which is the average state value. So the next thing we're going to look at is, say, the average reward. So that's another metric we can use, right? The average reward. So again, these metrics are just different ways in which we can represent our J theta, which is the scalar metric we're trying to maximize. So here we would have R pi is equal to, so again, we have a vector of our rewards. So this is a vector of one step rewards. So our immediate rewards, that's what this vector is. So essentially what we do is we take this vector, so let's say R pi of s, which is equal to the summation over all actions of pi a given s times the reward of s comma a, right? Which is essentially the average of our one-time steps, because again, if we're in a particular state, like there are different probabilities of getting actions and there are different rewards that are associated with those probabilities. And so this is simply a weighted average of our one-step rewards, right? So our final metric itself will actually look like this. So we would have R pi is equals to, again, our weights here that determine the importance of being in different states. So that's summation over d pi of s, R pi of s, which is equals to expected value of R pi of s, right? That's all this is. So that's another metric that we can use to define, to maximize essentially in this case. So let's open up a new page and look at that metric we could use. Okay, so another metric we could use is the state value of a specific state. Which we determine as essentially v pi of s0, right? So again, this is just looking at maximizing. Let's say we have our episode starting at a particular state every time. So we're trying in the long term to maximize the value of that state. That's what all this is. But again, this is just to help us identify the different kind of scalar metrics we could use to maximize it, but the objective is the same. We want to find values of theta that maximize these metrics, right? And these metrics are all functions of pi, right? So that's essentially the policy gradient theorem, right? So I'm not going to go further deep into this, but I just wanted to give that overview. But let's actually go into the most important part of the lecture, which is the policy gradient theorem. Right. So this is essentially the core of the lecture, to be fair. So what the policy gradient theorem says is that, what the question we're asking is, how do we actually take the derivative of j theta? Because as you can see, let me show you. Where did we write that? Here. where we say theta t plus 1 is equal to theta t plus the derivative of j theta t. So how do we actually go about taking this derivative, right? So this is where this theorem comes in, and what it says is that the derivative with respect to theta of j theta, right? Because this is the core component of our optimization objective. So this is proportional to the summation over all states of d pi of s times the summation over all actions of q pi s comma a times the derivative with respect to theta of pi a given s, right? So this is the policy gradient theorem, right? So of course, the question you might have in your mind is, how did this actually come to be, right? So we're actually going to go through the derivation and the proof of this theorem so that we better understand how it came to be and why we use this form of this equation. So let's actually get started with our proof, right? So the first thing we notice here is, okay, so let's say we're given v pi of s, right? So this is essentially equal to, say, the summation over all actions of pi a given s times q pi s comma a. And why is that the case, right? So let's say we have here a state s, right? And we have some actions that we can take from this state, and we end up in some different states, let's say s prime, right? So this diagram always helps us understand why we do things a certain way. So this might actually lead to the state, who knows, right? So these are the different actions. So this is action A1, action A2, and what we said is that, fine, there's going to be a probability of taking an action given that you're in some state, right? For each state, right? So if someone asks us, like, what's the value of the state here? Well, if there are only two actions, it's going to be, let's say there's action 1 and action 2, right? And we know the q values of this. So we know q pi of s given a1, and we know q pi of s given a2, right? And these are the only actions. So we're going to look at the probability of taking this action, right? So we're going to say it's the probability of a1 given s times this value times the probability plus the probability of this q value times the probability of a2 given s, right? So we take each of the q values and we multiply by the probability of taking them. That's essentially the value of a state. That's all there is to that. So what that means is v pi, now you know why v pi of s is equal to this term here. This is more like it's a recap type of thing because we've already looked at this before. So essentially we have this, which means the derivative with respect to theta. So here I'm going to not use like pi theta or anything. You can just assume that pi is a function of theta, right? So I'm just going to leave that notation out. So the derivative of this is equivalent to the derivative of the term on the right here, right? And you can see why that's the case. So, and this is essentially equal to the summation over all actions. So what is the derivative of this term? We're going to use the product rule, right? Because again, we can actually move the derivative on the inside. So we can actually write this as, let's say, summation over a of the derivative with respect to theta of pi a given s q pi s comma a. So we can essentially write this in this format. That's the point I'm trying to make here. So if we use the product rule, so this is the derivative of pi a given s times the original, which is q pi s comma a, plus the original, which is pi a given s, times the derivative, which is the derivative of q pi s comma a. Right? So this is what happens. We use the product rule here. And the next thing is we can say this is equal to the summation over a, over all actions, of, once more, the derivative of pi a given s, q pi s comma a, right? So plus pi a given s times the derivative, instead of q pi s comma a here, we're going to say the summation over s prime comma r of the probability of s prime comma r given s comma a times r plus v pi of s prime. So essentially what we're seeing here, this is essentially q pi s comma a. So we're saying these two are the same. And why are we saying they're the same? Well, it's again the same thing we've discussed before. So let me try to make room for this. Maybe up here is fine. So again, we are in a state, we're in an action, we take an action, right? We're in a state S, we take an action, and with some probability, we'll end up in some future state S prime or a different state S double prime, it doesn't matter. The idea here is that, okay, you're in a state, let me write it like that, you take an action, so in the process you get a reward, and you might end up in this S prime, or you might end up in this S double prime, right? So this is where this probability is coming from, whether we end up in this state or in that state, we've already talked about this before, times the reward we get along the way, times the value of v pi of s prime. So the value of this state is equals to the reward we get times the value of that state. That's essentially what this is. And it's just multiplying each state by the corresponding probabilities. So this part should be easy to understand if you've been following the lectures. If it's still confusing to you, you can watch the earlier lectures on MDPs. Should be lecture 2 and 3. And this should give you an idea of why this is the case. So having said that, let's continue. So this is equal to the summation over a of, again, we have delta pi a given s, q pi s comma a, right, plus pi a given s times summation over s prime comma r. So what we're going to do is we're going to move the derivative here inside. We'll move the derivative inside and just compute this using the product rule again. So we'll have the original ps prime comma r given s comma a times the derivative of v pi of s prime, because r doesn't depend on theta, so we don't need to actually make the derivative with respect to r here. So this is just a constant, plus r plus v pi s prime, which is our original, times the derivative of this is just a constant, so times 0. Alright, so what we end up with is a summation of a, right, let me actually put this here, derivative of pi a given s, q pi s comma a, plus pi a given s, right, times the summation over s prime of the probability of s prime given s comma a. If you remember from our lectures, we use this interchangeably, but essentially this is the summation of ps prime over r. So this is a summation of this term just over r. So that's why I'm writing it this way, right? Times the derivative of v pi s prime. Right. So something interesting happens here. What we were trying to find was the derivative of v pi s prime, which is equal to all of this, and somewhere in this derivative, we've got another derivative of v pi s prime. So we have got this like recursive like formulation, right, whereby v pi of s is actually determined by v pi of s prime, which is a value we do not actually know yet, right? And this has been pretty much constant with most of these algorithms that we've been looking at. So it's not really something that is new, right? But in order to actually express this better, let's actually take a step back, right? So let's take a look at the following. So let's say we're given p pi of s to x comma k, and we define this as the probability of transitioning from state s to x in k steps. So we're transitioning from state s to state x in exactly k steps. That's what this probability means, right? So for example, if k is equals to 0, this is the this would be the probability of transitioning under pi of transition from s to s in 0 steps, which is just 1, right? If k is equals to 1, right, therefore this is the probability under pi of transitioning from s to x in k is equals to 1 step, right? And what is this equal to? Well, this is the summation over all actions of the probability of a given s times probability of s prime given s comma a. Why is this the case? Again, let's go back to that diagram of ours. Let me use a different color. Where again, I'm just going to make the same point, and you'll see that the same point is sticking everywhere. So the question is, what is the probability of transitioning from state S, right? So from state S to state S prime, right, here. So let's say we can take, let me use a different color. We can use action 1, action 2, right? So if we take action 1 with some probability, we'll end up in S prime. If we take action 2 with some probability, we'll end up in S prime, right? And there is a probability that's associated with whether we're going to take action 1 and whether we're going to take action 2. So essentially what we're saying is, we look at the probability pi a given, or let me write it as pi a1 given s. This is the probability that from this state we'll take action 1, right? But if we take this action 1, what is actually the probability that will end up in S prime? This is represented by S prime given S, and we took action 1, right? So that's essentially what this probability is, associated with taking action 1. And then the same thing goes for action 2. So we add the same probability for action 2, which is what the summation term is here, right? We're just adding up the probabilities. So I hope that's clear to you. And again, this should be fair and familiar if you've been following the lectures. Now, when we look at k is equals to 2, right, this is the probability under pi, right, of, let's say, s to x and k is equals to 2. What this means is we're first going to transition to some intermediate state, right, before we actually transition to our state x, right? That's what this is. So what that means is the probability under pi of s x in two steps is equal to the summation over all s primes. By the way, in this case, s prime is an intermediate state. So that's p pi of from s to s prime in one state, and p pi of s prime to x in one step. One state, just one step. Right, so what this is saying is, for all possible intermediate steps, the probability of transitioning from s to x in two steps is equal to the probability of me transitioning from s to an intermediate step s prime in one step times the probability of me transitioning from that intermediate step s prime to x in another step, right? So we already know how we can express this when k is equals to 1, when k is equals to 0, right? So of course, we've defined our base cases, and we can essentially write this in a more general way to say the probability pi of s to x in k plus 1 steps is equals to the summation over s prime of p prime from s to s prime in k steps, right, times the probability of prime from s prime to x, in one step, right? That's essentially the formulation here. Let me try to highlight it to make it very clear. Right. This is essentially the result we're going to make use of in the future. You might be thinking, like, why am I making this derivation? But they're going to be important in deriving the policy gradient theorem itself. So I'm going to, let me set a new page. So, okay. We've actually looked at how we can come up with these derivations of probability of transitioning from state S to X in K steps. And this should give you an idea of, this is actually leading to us estimating the average amount of time that we spend in a particular state in a given episode, right? That's why we're computing these probabilities. But again, we're going to get to that in a moment. So let's let's go back to our equation here. So I'm going to assign, so this is our equation here. So I'm going to assign phi s to be equal to summation of all actions of the derivative of pi a given s times q pi s comma a, right? So phi s is essentially equal to this term here, you see here, right over here. So what do we end up with? So the derivative with respect to theta of v pi of s is essentially equal to phi of s, right? Which is the term here. I should indicate it here, that this over here is what we're calling phi of s, right? So this is phi of s plus the summation over all actions of pi a given s times the summation over all s prime of the probability of ending up in s prime given I'm in s and take action a times the derivative of v pi s prime, right? So this is the rest of this term here, right? But we need to add this like summation here to ensure everything is fine. So that's where we are now. And now we say this is equal to phi of s plus, so let's combine these summations, and we're gonna get the summation over s prime, summation over over a, since a linear operation, it's fine, of pi a given s times the probability of s prime given s comma a times the derivative of v pi of s prime. Right? But we see something interesting here. If you remember, we have this result over here. I should highlight this in pink. This result here that says the summation of all actions of these probabilities is essentially this term, the probability of transitioning from s to x in one step. We have the same term here. So what does that mean? Well, it means we can write this as follows. S prime times the probability under pi of transitioning from s to s prime in exactly one step times the derivative of v pi of s prime. Right? So again, this formulation is just coming from this pink term here. Right? They're essentially the same. So this pink term is this pink term. Right, these are the same, and we've already spoken about why that's the case, so it's fine. And next, we're going to say this is equal to phi of s plus the summation over s prime, right, of p pi s to s prime in exactly one step times. So the derivative with respect to theta of v pi of s is what we see here. So the derivative with respect to theta, again, I'm just assuming here, of v pi of s prime should be the same term, right? It's the same thing. So like I said, the derivative here is this term, so we just rewrite this term in here, and that gives us f. But since our input is s prime, it's phi of s prime, right, plus the summation over s double prime, right, of p pi, the transitioning from s prime to s double prime in exactly one step, right, times the derivative under theta of v pi s double prime, right? So we have all of that. Well, this is interesting. Again, we started with the expression in v pi of s, and then we had it in v pi of s prime. Now we have it in v pi of s double prime. But let's just simplify it a bit so that we can make our conclusions later on. So this is equal to phi s plus the summation over s prime of p pi transition from s to s prime in one step, right? So this, we multiply this by phi of s prime plus summation over s prime of p pi. Again, what we're doing here is essentially we multiply this plus this times this plus this times what's inside. So we have p pi, where were we? S to s prime, yes, this is s to s prime in one step, times the summation over s double prime of p pi s prime to s double prime in exactly one step, times the derivative under theta of v pi s double prime. Okay, so this is getting pretty long. All right. So we just multiplied this times this plus this times that. That's all we did here. So let's simplify that further. So this is phi of s plus summation over s prime. So this pretty much stays the same, right? S to s prime in one step times phi of s prime plus, now this term here we're going to combine, because if you look over here, we said if we have p pi s to s prime in k steps times p prime from s prime to x in 1 steps, this gives us like p pi of s to x in k plus 1 steps, right? So here we've got p pi goes from s to s prime in 1 step, then it goes from s prime to s double prime in 1 step. So we can essentially write it as summation over, let's say, s double prime, that p prime goes from s to s double prime in 2 steps, right? So because s to s prime in 1 plus s prime to s in 1 is s to s double prime in 2, right? So this is just coming from what we have here, this result here in red. That's where it's coming from. So having said that, this is times the derivative under theta of v pi s double prime, right? So this is where we are with our expression. And the next step is to expand this further. So as you can imagine, we can expand this as long as you essentially want to, but we can have, this is equal to, so let's rewrite this expression. So I'm going to say summation over s of p prime from s to s in 0 steps times phi of s. And let me write this in the phi of s in a different color here. So let's say times phi of s, right? Plus, and the reason why we can do that is this probability is just, this is 1 actually, from transition from s to s prime. So these terms here are the same. So plus the summation over s prime of transitioning, which is the second term over here. So that's from p prime from s to s prime in 1 step times phi of s prime, right? Plus the summation over s double prime from p pi s to s double prime in 2 steps times phi of s double prime, right? And this keeps on going, and then we're going to have plus summation, let's say s to the k of p pi s to the k prime, comma k, times phi of s, whatever k is, right? And this goes on and on, right? So this is how we're now writing our expression. And essentially what this boils down to is a summation over x, which is an element of s, times the summation from k is equals to 0 until infinity of p pi s to x in k steps times phi of x, right? That's our final expression here. So essentially what we can do is say, actually, the derivative of, say, j theta, which is equal to, let's say, the derivative of v pi of s0. Let's say this is the metric we're trying to maximize, because we already discussed a couple of metrics we could use, from average state value to average reward value to just the long-term value of starting in the state and so on. So this is essentially equal to summation over s, summation from k is equals to 0 until infinity of p pi from, since we're starting from s0, probability of transitioning from s0 until s in k steps, so we're just writing this more generally, times the phi of s, right? This is essentially the result. Well, I mean, we're not there yet, but we're getting there. Again, remember this probability is the probability of transitioning from state, say, S0, to state S in exactly k steps, right? And we already looked at how we can compute that probability, right? Okay, so we continue. So what we know is that we've computed what this derivative essentially is. Let me write that down again on this new page, right? I could copy and paste, but whatever, let's just get this done with. V pi of S0 is summation over S, summation from k is equals to 0 up to infinity of p pi of from S0 to S in k steps times phi of S, right? So what we can write this as, this is equal to the summation over S, right, of this term. So, and we multiply this by phi S. Well, I don't know what the Greek letter this is, but anyway, you get the point, where this term is equal to the summation from k is equals to 0 until infinity of p pi from S0 to S in k steps, right? So we are just replacing this by this term, and this is essentially representing the time that we spend in state S, right? So this is like how much time we're actually spending in the state, in this particular state, which is why we're computing this. Because as you can tell, this is not an actual probability that sums up to 1 or anything. But we can convert it into a probability distribution, and we can do so as follows. We can say this is equal to, so we're going to have summation over S of this term divided by summation over S of this term, right? And we're going to multiply that by the summation over S of phi of S, right? Which is what we have here. So this term is essentially equal to 1, right? And this is essentially going to give us summation. So we're doing this so that we get a probability distribution here, which would be, so if we put this term inside, we would have summation over S. Let me use a different color here. Times, right, so that's here, times summation over S of this term over summation over S, because we just moved this term inside, of this term times phi of S, right? So essentially what we end up with is, so essentially this term, we've converted it into a probability distribution, right? Which we said we can denote by d pi of S, right? Because, which was just like how important each state is and so on. That's how we said we could denote that. And what we end up with is, well, essentially this is indicating, again, the average length of an episode, right? So this term, like we said, we can replace this by d pi of S. So what we end up with is equal to, say, summation over S of this term times this term, which we termed as, well, essentially d pi of S, right? So that's summation over S of d pi of S, right? Actually, this is the stuff inside, but anyway, you get the point. Right? Times phi S. What was phi S? We defined phi S a long time ago, and we said it was equal to this term here, so let's just write it back down, right? And this is let's say summation over a of the derivative of pi a given s times q pi s comma a, right? That's what phi s is. And since this term is just a constant, so we can say this is proportional to the summation over s of d pi of s times the summation over a of the derivative of pi a given s times q pi s comma a. And just like that, we have more or less derived the policy gradient theorem. So this is what we've been estimating all this time. So now you have a better idea of like where this is actually coming from and how this theory came to be and how we actually compute our gradients. So the most important things to capture is, one, we need to parameterize our policy, right, by some parameter theta. And then after that, we need to decide on what metric we want to maximize. And then here we went about how we would compute the gradient of such a metric, right? And we are going to use this result in our future lectures to derive more policy gradient algorithms. So we will start with an algorithm called reinforce, and we're going to add a baseline. Then we're going to look at some actor-critic methods. And using these algorithms we've learned, we're actually going to implement them in our current like self-driving car simulator and see how they perform compared to the value-based methods when we get there. So the next thing we need to think about is how can we actually express like our parameterization here. So for instance, we're talking about probability of a given s, which is parameterized by theta, right? So we can actually express our numerical preferences of our actions using the following function, right? So let me write this somewhere else. So we can use something like hs comma a comma theta to just indicate like which actions we prefer over others. So this essentially could be something like, if we use something familiar, for instance, it could be theta transpose xs comma a if we're thinking about, if we're dealing with linear functions, but if the theta here could be an entire neural network or whatever. But the point here we're trying to capture is that we could have a softmax in action preferences. So one way in which we could essentially represent this function is to say it's e to the h s comma a comma theta, right, divided by the summation over, let's say, b of e to the h s comma b comma theta, right? And this is essentially like our softmax. Let me write that down. This is softmax in action preferences, right? And the advantages of such a parameterization of policy gradient method in general is that this approximate policy can eventually approach a deterministic policy as long as we have got some temperature parameter that is controlling that, whereby in epsilon greedy methods, of course, there's always like a probability associated with taking a random action to some extent. But the main point here is, well, if we have this kind of parameterization, sometimes the optimal policy might be stochastic, right? The optimal policy might not be just act like in this way, but act in this way with a probability of x, or act in this way with a probability of y. So the optimal policy might be stochastic, and this kind of parameterization and the usage of policy gradient methods is useful in that regard. And so there are quite a few advantages of using these over like value-based methods. Also, when you're dealing with continuous functions as well, like you can estimate direct continuous values, as we'll see in the future lectures. So the point of this lecture was just to introduce the idea behind policy gradient methods introduce the policy gradient theorem and its derivation. And hopefully this lecture will be helpful to you. And in the next lecture, we're going to start looking at our first policy gradient algorithm called reinforce. So see you in the next lecture. Thank you.